Welcome to a Math Shorts Extra. We're going to delve a little bit deeper into the topic that we looked at in episode 10, that is square roots, seeing how to deal with some extra things and get some finer approximations or use these tools to get a little bit better results. So, for one thing, how do we deal with larger numbers? We saw that to do an approximation, we kind of had to know what two perfect squares our number fell in between. But what happens if I'm dealing with a number like 2023? We might not know all the perfect squares to allow us to find out which two it's between. But there's a trick that we can use that will allow us to only really have to know the perfect squares of the one-digit numbers, 1 squared, 2 squared, 3 squared, all the way up to 9 squared. And that is, if we take this number 2023, and instead of working with it, let's consider the number 20.23, which I just got by taking 2023 and dividing by 100. And the reason I'm dividing by 100, not 10, is we can use some properties of square roots. The square root of a division is the same as dividing the square roots, and the square root of 100 is 10, which means that if I can find out something about this, that's actually going to be 1/10 of the one that we're after. So to find out the square root of 2023, we just work out this guy and multiply it by 10. So how would we do that? Well, 2023 is between 4 squared, which is 16, and 5 squared, which is 25. If we look at the extra stuff, it's bigger than 16, so 20.23 minus 16 is 4.23. And then we could do the same thing. We said we got something with sides 4 and 4, so I've got 8 spots. So square root of 20.23 is going to be less than 4 and 4.23 over 8, which is kind of an ugly fraction. That's okay for now. On the other side, it's going to be less than 4.23 over 9, one extra. Then if we want, we can do a little math to make these things nicer. I can multiply this by 100 and 100 to get 423 over 800 and 423 over 900. And then keep in mind that this thing is really this guy over 10. So now I can actually go through and multiply by 10, do a little bit of cleaning up. And if I do that, I find out that the square root of 2023 is somewhere between 44 and 7/10 and 45 and 23/80. So I've managed, after one sort of go of this, to get an idea of basically to a whole number that is between 44 and 45, somewhere in there. But now that we know that, we can actually do it again, knowing that it's a little bit bigger than 44 squared. So if I know that 2023 is a little bit bigger than 44 squared, we can say, now imagine if I had 44 squared on each side, I'd have 2023 minus 44 squared, which is 87. I've got 88 blocks, 44 and 44, to fill up. So my square root is going to be somewhere between 44 and 87 over 88 and 44 and 87 over 89. And if we work those two things out, 44 and 87 over 89 is 44.977. And on the other end, I get 44.988. I get a pretty good approximation of the square root of 2023. And if we were really ambitious, we can tell here, just by looking at the first decimal place, it's going to be 44.9 something. So I could say, oh, 44.9 squared is less than 2023, and I can go back and do the same process. I go 2023 minus 44.9 squared, get something, do the same sort of process. And I could do this over and over and over, and sort of each time I would do it, I'd get one more decimal place. So here I'm good to 1 decimal place. If I do it again, I'd be good to 2 decimal places. If I do it again, and so on down the line. So to deal with bigger and bigger numbers, we just have to do more steps, and we kind of get 1 digit, and sometimes more, of our square root along the way. So when we're dealing with a big number, we start from the decimal and we kind of block the digits together in blocks of 2. So I make blocks of 2 all the way. The last block might be 1 or 2 digits. So if I'm dealing with the square root of 31,415, I could block it into a 3, a 1, 4, and a 1, 5. And then we would do the same sort of thing as before. I'm going to put my decimal right before the last block here. And I'm going to consider, instead of 31,415, I'm going to consider 3.1415. And we'll go through our process. That's between, well, it's this thing over 100 squared, which is between 1 squared and 2 squared. So I know I'm going to start with 1 squared. My extra is going to be the 3.1415 minus 1 squared, which is 2.1415. So the square root of 3.1415 is going to be 1 plus this extra divided by 2, because it's a 1 square, 1 here and 1 here. And on the other side, it's going to be divided by 3. And then we can kind of do like we did last time and say, well, if I multiply everything by 10, that actually moves the decimal in here by 2, because we're multiplying by 10, which is the square root of 100. So if I multiply through by 10, clean up these decimals, or clean up those fractions and reduce, I get the square root of 314.15 is between 17 and 83 600ths and 20 and 283 400ths, which tells us that 17 squared is less than 314.15. And that would be our next starting point. So starting from there, I'm going to start with 17 by 17 squared. I want to approximate 314.15. So I subtract 17 squared, which gives us 25 extra. So I'm going to be, I've got 17 and 17. I've got 34 spaces to fill up with this 25.15. So I got 17 plus 25.15 over 34. If I had 1 extra slice for everything, so I cut it into 35 slices, it's going to be a little bit too small. And then we can go through, multiply everything by 10 to bring us to the right spot, clean up the fractions, and I get 300, our square root of 31,415 is between 177 and 13 over 70 and 177 and 13 over 68. So now I know that it's 31,415 is a little bit bigger than 177 squared. I can do my process again, subtract 177 squared from our number to get 86. So I'm going to have 177 on each side of our square. So I'm going to need twice that. So 354 chunks for everything. I've got 86 things. So I'm going to be between 177 and 86 over 354 and 86 over 355. And if we work those things out as decimals, look at what we get. We're between the number 177.242253 and 177.242937. So I've actually got something that's good to 3 decimal places, which is pretty good. After 3 goes, we've managed to get a very good approximation. And if I wanted to go one more step, my next starting number could be 177.242, and then do the same sort of thing, and I'd get an even better approximation. So let's do what looks like a little bit of a detour. We're going to consider the square root of 1 plus x, where x is some number between 0 and 1. So thinking of our geometric model, 1 could be a square whose side is 1 and 1. The extra area, that's an area of 1. The extra area could be a rectangle that's 1 unit long and x units wide to give us our x. So together we've got an area of 1 plus x. And we're trying to find the square root, so we want to take all this area together and see how big of a square we can get. So, like we've done before, from this extra area, we'll kind of cut it in half and put each half on the sides. We see that this is too small. The original thing was 1 by x, so this is going to be x divided by 2. And we see that our root of 1 plus x is going to be less than 1 plus x over 2, because we don't have enough to fill in this space. Now, rather than do like we usually did and go and cut it into 3 pieces, which gives us more than enough, we're going to concentrate on that missing chunk. So since this is x over 2 and this is x over 2, the area of the little piece is x over 2 times x over 2, which is x squared over 4. And what we're going to do now is we're going to shave a little bit off these rectangles to give us our x squared over 4. Now, I'm shaving off 2 chunks, so each chunk has to make up half this area. So each chunk has to be x squared over 8. And if we look at this, since this is 1 unit long, if the area is x squared over 8, the other side length is going to be x squared over 8. So if I shave those 2 pieces off and use them to fill up this part in the middle, I get something that looks like this. And now if we look, I've got a square whose side was 1 plus x over 2 minus x squared over 8. And we can see we've got a little bit too much here. So again, we can get another approximation that this thing is going to be bigger than 1 plus x over 2 minus x squared over 8 because I've got this little extra chunk. And if we think a little bit further, if I slice this along here, it's going to be x squared over 8 times x over 2, which is x squared over 16. I could take that chunk and put it in here. This chunk wouldn't quite go to the edge. It wouldn't quite be x squared over 16 because I've taken off the corner and I'm missing it from here. So if I put an extra x squared over 16, I'm not going to have enough to fill up the square, so I could go the one step further to get x squared over 16 is going to be too big. And again, I could go back and forth. So I have an approximation for this function. Now, for those that know a little bit of calculus, or later on you'll see in calculus, there's a thing called a Taylor series of a function about a specific point, which means that we can take a function and we can approximate it, no matter what that function is, by saying, well, let's just say that it's equal to f at this particular value. Then our new function will match when x is equal to a exactly. But beyond that, it could be different. So I'm going to add in something else. I'm going to add the derivative times x minus a. If I put in x equals a, this is still 0, and I'm still at f at a, which is going to be the same. But if I'm not, then if I take the derivative of this function, the derivative of this function is going to be f prime of a, which will match the derivative at that point. And it means that if I'm really close, the rate of change is going to be close to this. So this will give us a good approximation of what it's going to be. Now if I add in another term that's the second derivative times x minus a squared over 2 factorial, then what happens is if I do the second derivative is going to match at x equals a. And if I keep putting in terms, the third derivative times x minus a cubed over 3 factorial, the fourth derivative times x minus a to the fourth over 4 factorial, and so on, I'm going to end up with a function that at x equals a matches the original function and all of its derivatives. So it behaves exactly like that function does at that particular value. And because it's behaving exactly the same, what it means is if I pick a value of x that's close to a, then this thing is going to be close to that value. Now, depending on how many derivatives we take, the more derivatives, the better the approximation is going to be. The closer I am to a, the better the approximation is going to be. Now, mathematicians are all about making things easy, so we could write this as in summation notation. But if I make a equal to 0, then this Taylor series is called the Maclaurin series. And then what will end up happening is all these x minus a's just become x's. And so I get f of x is equal to f of 0 plus f prime of 0 times x times f double prime of 0 over 2 factorial times x squared, and so on down the line. Now we're interested in square roots. Now, unfortunately with square roots, the derivative of the square root function at 0 and all the second and third and fourth aren't defined. So that kind of puts something into the mix. But if instead I look at the function the square root of 1 plus x, then when x is equal to 0, the derivative exists, and so on. So that's kind of why we were looking at that 1 plus x. And look what happens if we take a equal to 0. So we do the Maclaurin series for this. This is what we get, which was exactly what the first few terms that we saw before. So let's take a look at this a little bit closer. Okay, so let's see this Maclaurin series in action with the square root of 2. So this would just be f of 1, which is the root of 1 plus 1. So we're going to get the following approximations, and we know that the square root of 2 is 1.4142, ... So we'll get an idea of how well this approximation using the Maclaurin series for root of 1 plus x is. So we'll just sort of do it a term at a time and see what happens. So the first term is just 1, which is less than the square root of 2. If I add the next term, it's 1/2, which gives us 1.5, which is a little bit bigger than the square root of 2. The next term is going to be minus 1/8, which gives us 11/8, which is 1.375, which is a little bit less than square root of 2. The next term is plus a 16th, which gives us 1.4375, which is bigger than the square root of 2. The next term leaves us to 1.398, etc., which is a little bit less. So as we go back and forth with the plus and minus, I go a little bit bigger, a little bit smaller, but I'm kind of zeroing in. But if we look at our square root of 2 is 1.41, and if I look at my approximations, 1.5, 1.37, 1.43, 1.39, I've gone through 1, 2, 3, 4, 5 terms of our expansion, and I still haven't quite got the first decimal place. Now, the last two round to 1 decimal place, but it seems kind of slow. But if we looked at that series, we saw that this thing works for x's really between -1 and 1. And so we're kind of at the upper limit here. So as a result, square root of 2 this way is going to be sort of the slowest possible converging that we get. If I can use an x value that's closer to 0, I'm going to get something that goes a little bit faster. Whoop-de-doo. So I'm going to be able to approximate things between close to 1. Well, let's see how we can use this to our advantage. Imagine I wanted to do something like the square root of 101. I could write the square root of 101 is 1 plus 100. Well, we can't use x equals 100. That's outside of our range. But if we rewrite this as 100 times 1 plus 1/100th, and now I can do the square root of 100 is 10. So I can write this as 10 times the root of 1 plus 1 over 100. 1 over 100 is small. And so I can write this as 10 times f of 1/100th. And if I do the expansion for 1/100th and multiply our result by 10, I should get an approximation for root of 101. So let's see what happens. Root of 101 is 10.0498 and so on. So the first term is just 1, so I get 10 times 1, which is 10, which is a little bit too small. The next term is 10 plus 1/100th over 2, which gives us 201 over 20, which is 10.05, which is not bad. It's a little bit too small. The next term, I'm going to add this 1/100th squared over 8. If we simplify that whole thing, I get 80,399 over 8,000, which gives us 10.049875. And if we look at this, 10.04987562, that's pretty darn close. So this one converges a lot quicker because I'm using this value close to 0. And so if we use sort of the same trick that we did earlier for approximating big numbers, that is sort of multiply by something. And here, if I find sort of the closest square root and divide that thing out, I'm going to be able to get some approximations. And especially if I'm close to a perfect square, it's going to be pretty good. But sort of the worst I would really have to do is be off by 0.5, because if I was getting close to the next one up, I could actually use it as a minus and use the next highest up one and use a negative. So those things, because I'm using fractions here, as we start doing powers of them, they shrink quicker and quicker, and we get better and better approximations. So I hope that you enjoyed this extra little chunk of Math Shorts.